Consider the hybrid function h of x with the following rule. For part A, we want to evaluate h when x is -3. So if we have a look at the subdomains within the function h, we can see that -3 exists for the top rule. Therefore, h of -3 will involve substituting x into the quadratic equation. So we'll have -3 plus 3 squared, and -3 plus 3 is 0, and 0 squared is 0. So h of -3 simply equals 0. So that is the answer to part A of this question. For part B, we're asked what values of A will h of x have two x-intercepts? And this is one of those questions that you may come across from time to time, where it's actually better to do a later part of the question first before answering this. So I'm actually going to leave part B to answer in a moment's time. So we're told at a basic level a hybrid function is said to be continuous if the entire graph can be sketched without removing your pen from the paper. That is, the two different graphs intersect at the join, so there's no gap or jump between the two graphs. So for part C, we have if a equals -1, the hybrid function is now given by this rule. And we're asked to sketch the graph of the hybrid function, clearly labelling any endpoints, turning points, points of intersection and axial intercepts with their coordinates. So that's quite a bit to unpack, so we're just going to start by graphing x plus 3 all squared in blue. And we're going to sketch it between -6 and -1 for the x values. So finding the key features of that, we need to find the endpoint at -6, so we sub -6 into the function of h, which will give -6 plus 3 all squared, which equals -3 squared, which is +9. Then we also have the endpoint at -1, which is going to be -1 plus 3 squared, which equals 2 squared, which equals 4. So if we consider what we also know from part A of the question, we know that h of -3 equaled 0. And in this form, we know that that's the turning point of the parabola at -3, 0. So if we put a scale on, this might be -6, so that could be -3, and this could be -1. And we know that it goes from -1, 4, and that's a coloured in dot because we have the equals to inequality here. And then it goes through that point and then up as high as 9 up here. And that point's also included, so it's coloured in dot because of the inequality symbol here. So that's the parabola with a rule y equals x plus 3 squared. Now just to finish this off, that turning point has a coordinate of -3, 0. Then we also need to sketch the line y equals -x plus 3, which we'll do in red, and that's for all x values greater than -1. So if we sub into h, if we sub in -1, even though it doesn't exist at that point for the straight line, this is the value it's going to approach or get really close to. So we'd have -1 plus 3, which equals 1 plus 3 is 4. So that's going to start at this point, and then inspecting the rule, we can see it has a y-intercept of 3, and it's a straight line with a -1 gradient, so it's going to look something like that. So the key features of this graph are going to be the y-intercept, and that's at 0, 3, and you could substitute y equals 0 and solve for x, and you'd get +3, 0 here for the x-intercept. So that is the graph of the hybrid function h of x. So that line in red was y equals -x plus 3. So now that we've sketched that graph, we're going to go back and consider B. And that was for what values of A will h of x have two x-intercepts. So if we do a really quick sketch of what we just had before on the previous slide, we had this section of the parabola which would always exist no matter what the value of A is. So now we need to think about what A really does to the graph, and A is the gradient of that straight line. So if it's the gradient of the straight line, as long as it's negative and it passes through this point +3 because that's the y-intercept, as long as it's negative, we'd have graphs that look like this that will eventually have x-intercepts. However, the minute you have a 0 gradient, there'd be no intercepts, and there'd be a series of gradients here that don't give an x-intercept. And that is until you've reached another gradient here, which did give an x-intercept, at the point where x equals -1, so -1, 0. And the gradient that would be responsible for that would be run 1, rise 3. So the gradient of that would be run 1, rise 3, so it would be a gradient of +3. So now we need to summarize what we've found. So we could have all a values being negative, so a being negative will give 2 x-intercepts. And then there's also a case of if a is greater than 3, so it's a nice positive steep gradient, it will also give 2 intercepts. And just to elaborate on that second dot point, if we drew another gradient here that was maybe +4, that graph would come down and it would have another x-intercept just here. And the same would be true for +5, etc. So that would go on and on. So for part C, part 2, we want to hence state the range of the hybrid function when we considered a equaling -1. So the graph that we drew before has been reproduced using a computer, and we can see that the range has a smallest y value of -infinity, because that's what this graph in red would go on to approach, and the largest y value is at 9, and that has a square bracket, and that is due to this value up here at 9, which is included. And the last part of this question says state the angle created by the line y equals -x plus 3 and the positive direction of the x-axis, and that's being drawn as this theta value over here on our diagram. And now because the gradient is -1, we know that this is a 45-degree angle that's wedged in between the x-axis and the line. So therefore the angle that we're asking for, the obtuse angle, is 135 degrees. So that is the answer to that part of this question.